This is our second lecture on Laplace transform. In last lecture, we discussed about definition and some examples. Now here we'll see of which functions we can find the Laplace transform. So sufficient conditions for Laplace transform. If f of t is sectionally continuous in every finite interval and of exponential order, then we can find the Laplace transform of that function. Don't worry about these two things. Question is whether we can find the Laplace transform of every function. So answer is not. Those functions which are sectionally continuous. What is the meaning of sectionally continuous function? Let's see this figure. This function is defined on the interval a to b. Now at the points, see here, at points c and d, what we can say about continuity of this function? So at c, left hand limit is this value and right hand limit is this value. So left hand limit is not equal to right hand limit, so this function is not continuous at c. Similarly at point d, left hand limit is this one, right hand limit is this one, so this function is not continuous. But on this interval or on this section, this function is continuous. Similarly from c to d, this function is continuous. Similarly from d to b, this function is continuous. Such type of function is called sectionally continuous functions. And exponential order means this is the definition. So those functions which are sectionally continuous and of exponential order, we can find the Laplace transform these functions. So what is the example of function of which we are not able to find the Laplace transform? So see here. So this is the function f of t equal to e raised to t square. So we are not able to find out Laplace of this function. The next part is, so some standard formulas are there. Remember this table. This table is very important. So when f of t is 1, its Laplace is 1 by s, where s greater than 0. When f of t just t, its Laplace is 1 by s square. When f of t is t raised to n, its Laplace is gamma of n plus 1 by s raised to n plus 1. And when this n is in positive integer, gamma of n plus 1 is nothing but n factorial. Next formula is Laplace of sine at, a by s square plus a square, where s greater than 0. Cos at, s by s square plus a square. Then e raised to at, 1 by s minus a, s greater than a. Sine hyperbolic at, a by s square minus a square. Cos hyperbolic at, s by s square minus a square. So remember this table. This table is very important. Here I will prove this third and seventh formula for your reference. How this formula came. So first see the seventh formula. So Laplace of sine hyperbolic at. We know the definition of sine hyperbolic at. The definition of sine hyperbolic at. So e raised to at by at minus e raised to minus at by 2. So by linearity property of Laplace, we can take 1 by 2 outside the bracket. So 1 by 2 outside the bracket, Laplace of e raised to at minus Laplace of e raised to minus. This is because linearity, Laplace of c1 f1 plus c2 f2 equal to c1 Laplace of f1 plus c2 Laplace of f2. Now, by this formula, Laplace of e raised to at is 1 by s minus a. So here, Laplace of e raised to at 1 by s minus a. Laplace of e raised to minus at 1 by s plus c. Taking cross multiplication, you will get So solve this. Like s plus a minus s plus a divided by s minus a into s plus. 1 by 2, 2a by s square minus a square, a by s square minus a square. Now, Laplace of t raised to n by definition 0 to infinity e raised to minus st and t raised to n. Now, so we need to use substitution. St is u, so t is u by s, so dt is du by s. And limits are 0 to infinity. So Laplace of t raised to n is 0 to infinity e raised to minus u by s raised to n du by ds. So see here, e raised to minus u to the power n divided by s to the power n. Here, s to the power n, this s to the power n, and this s to the power n plus 1. Taking it, integration is with respect to u, so s to the power n plus 1 is constant, so we are taking it outside the integration. So this becomes 1 by s to the power n plus 1, 0 to infinity, e raised to minus u raised to n is here, so we'll add plus minus 1. Now see the definition of gamma function. Gamma of x equal to 0 to infinity e raised to minus t to the power x minus 1 dt. Now in place of t we have u, in place of x we have n plus 1. So by this definition, value of this integration is gamma of n plus 1. And we know the property of gamma function. When this n is a positive integer, gamma of n plus 1 is n factor. So Laplace of t raised to n is gamma of n plus 1 by s raised to n plus 1. And if n is positive integer, it is n factorial by s raised to n plus 1.